A business is rarely a static entity. Behind the polished corporate facade, a firm's employment pool is in a constant state of churn, a continuous flow of hiring and firing. When we look at the raw data, an empirical paradox emerges. The net variations in a firm's total headcount are vastly smaller than its gross flow of labor. High volumes of hires and separations are constantly masking a relatively stable total employment number. Looking at these overlapping data points reveals two counterintuitive facts. Even when a firm is aggressively shrinking its overall workforce, the data shows they are still actively hiring. Conversely, firms experiencing rapid growth continue to record substantial numbers of separations. To understand the economic logic driving this real-world churn, we have to strip away the chaos. We need to build the mathematical foundation of how firms actually calculate their demand for labor. In economics, labor demand is defined as a derived demand. Firms do not inherently want employees. They want to produce goods and services for consumers. The desire for a worker is entirely derived from the market's desire for the product. We can model this in the short run by setting up a strict optimization problem. Assume capital, the machinery and buildings, is fixed. Labor is variable. A firm's profit equals its total revenue minus the costs of these two inputs. To find the optimal number of workers, we take the derivative of the profit function with respect to labor and set it to 0. Doing this isolates the fundamental condition for hiring. A rational firm will hire workers exactly up to the point where the marginal productivity of the last person hired equals their real wage. If they produce more value than they cost, they get the job. This chart plots that physical reality. The green line represents the production function. Because the firm has a fixed amount of capital, adding more workers eventually creates a bottleneck. The law of diminishing returns forces the production curve to flatten out. The real wage is represented by the slope of these straight black profit lines. Maximum profit occurs exactly at point E, where the profit line lies perfectly tangent to the curved production function. This tangency point mathematically proves why the labor demand curve slopes downward. If wages drop, the slope of the profit line flattens out. A flatter line pushes that tangency point further to the right, meaning the firm optimizes its profit by hiring more workers. That model assumes perfect competition, where the firm can sell infinite units at a static price. But what happens to hiring if a firm has monopolistic control over its pricing? If a powerful firm produces more goods, it is forced to lower its prices to sell the excess inventory. To find the new hiring condition, we must use the product rule to calculate the derivative for profit, accounting for a price that actively changes with output. By factoring out the price variable, we can rewrite the equation in terms of the elasticity of demand. This introduces the concept of a firm's markup, the premium they charge over their marginal cost. Market power actively restricts hiring. Selling extra units produced by a new hire requires lowering prices for all existing units. The extra revenue generated by a new worker is strictly lower than their actual production value. If we extend our timeline to the long run, the rigid constraints disappear. Capital becomes fluid. Machines can replace humans. The firm now faces a two-stage problem, beginning with minimizing costs for a specific target output. This graph maps that choice. The curved Isoquant line represents every combination of capital and labor achieving the same production target. Overlaying the budget constraint as a straight isocost line, the cheapest way to hit the target is the tangency point E. At this optimal point, the firm's marginal rate of technical substitution perfectly equals the ratio of wages to capital costs. We can calculate this relationship using Shephard's lemma. Taking the derivative of the total cost function with respect to wages yields the firm's optimal labor choice, isolating the exact conditional demand for labor. The math guarantees a strict inverse relationship. Assuming a firm optimally resorts its machines and workers, its conditional demand for labor will always decrease as the price of labor rises. We have the theoretical rule, but to apply this in the real world, we need to know the magnitude. Precisely how responsive is a firm's employment headcount to a sudden shock in wages? Mathematically, total wage elasticity is split into two distinct forces, the substitution effect and the scale effect. The substitution effect dictates how many workers are swapped out for machines. The scale effect dictates how much the firm cuts back on production entirely, shrinking the overall scale of the factory due to higher operating costs. Measuring this in real time faces a severe endogeneity problem. Highly productive firms naturally hire more people, and they also pay higher wages. This creates a false correlation that obscures the true elasticity of demand. To solve this, economists search for exogenous shocks. A perfect example is the 2008 French zero-charges natural experiment, temporarily cutting total labor costs by 12% specifically for small firms with under 10 employees. This chart graphs the density of firm sizes around the policy cutoff. The smooth progression of dots crossing over the red 10-employee threshold proves firms did not artificially fire workers to shrink below the line and qualify for the subsidy. The data is clean. Using a difference in differences analysis, this graph shows the log wage differences remained parallel between treated and untreated firms. There was absolutely no wage inflation. Yet the eligible small firms saw a massive 0.8% jump in employment growth. We can now calculate the real-world elasticity. Dividing the 0.8% employment increase by a firm must calculate the discounted present value of infinite future profits against the immediate penalty of changing its headcount today. These friction costs do not scale linearly. Equation 2 specifies them as a quadratic function, meaning the financial penalty rises exponentially with the absolute size of the adjustment. Mass layoffs and mass hiring sprees are punishingly expensive. By taking the first-order condition of this intertemporal problem, we arrive at the Euler equation. Notice how the derivative links period t directly to period t plus 1. The economic logic here is brutal and precise. A firm will only hire a worker today if the immediate marginal benefit covers the net marginal cost across the rest of time. This chart plots marginal productivity, where firing is drastically more expensive than hiring. Between the upper hiring and lower firing thresholds lies a vast dead zone. If productivity falls inside this vertical gap, the horizontal line proves the firm refuses to alter its workforce. This inaction zone is the mathematical proof for labor hoarding. Firms will willingly absorb short-term losses and retain unproductive workers during a recession. They do this because waiting out the shock is mathematically cheaper than triggering the devastating frictions of firing and rehiring.